Now I'm going to cover more on why the representations are valid. So by that I mean we have seen the first line is true, right? By that we mean I'm going to show you why the Maclaurin series, the representation of e to the power of x, indeed converges to e to the power of x. The same thing is true for sine of x and cos of x, and even for inverse tan of x. I'm going to tell you why in some more details. Okay. But before we do that, we need to cover something called convergence tests. Convergence test. The first test I want to mention is the test on screen. It's called the ratio test. The ratio test. Okay. For any series, it's a test determining when the series is convergent, under what condition the series is convergent or divergent, or in some cases gives no information. Okay. In order to use the ratio test, you compute the limit of the ratio of the two consecutive terms. By that we mean the term I plus 1, the term I, you compute the limit of the absolute value of that ratio. If the limit is equal to L, and L is a number less than 1, and then you can conclude the series is convergent. You just know the series is convergent, but it's not giving you converges to what number. Okay. And also if the value of L, the value of the limit is greater than 1, then you can conclude the series is divergent. If the value of L, the limit is equal to 1, it gives you no information. You cannot use the value equal to 1 determine if the series is convergent or divergent. Okay. We'll show you a simple example. Now for instance, to determine the series converges or diverges, to identify term I. In this particular case, term I is 3 to the power of I over I factorial for all I. And of course I runs from 0 to infinity. Okay. And then we compute the limit of the quotient. Now watch. Term I plus 1 is determined by I value of I plus 1. So you have the numerator in here. Wherever you see I in here, you replace I with I plus 1. That's how you get term I plus 1. Okay. Likewise, on denominator, you have term I. Now we take the limit of the absolute value of the ratio. That's why we call it the ratio test. And then, so because all the numbers are positive, all the numbers involved in the numerator and the denominator are positive, I can get rid of the absolute value notation, right? And then simplify a little bit. That's the whole numerator. You interpret that big bar as a division. You invert and multiply. Invert the numerator and the denominator and multiply. Okay. Simplify. You cancel out the 3 to the power of I from the numerator and the denominator. There remains a 3 on the numerator. And likewise, you cancel out I factorial from the numerator and the denominator. There remains I plus 1 on the denominator. And then we take the limit as I goes to infinity. It means as I, the index, gets larger and larger positive. You can see the quotient gets tinier and tinier. I mean, getting closer and closer to 0, right? So you see the limit is equal to 0. Because 0 is less than 1, the series converges. Okay. So that's why this series is convergent. Again, you do not know what number the series converges to. It just tells you the series converges to some number. Okay. Actually, in this particular case, the series converges to e to the power of 3. We're going to see that. I think we have seen that. Okay. So we're just trying to prove it. I will show you one more question using the ratio test. So this time you have a variable in here. Now the question is, for which values of x does the series convergence? For which value of x does the series converge? Okay. The same idea. In the question we just did, we had a particular case of this question when x value is 3. So do you see that? When x value is 3, this question becomes that question, right? The same idea, actually. Again, identify ai, term I, okay. And then you try to compute the limit of the absolute value of the ratio. The ratio is taken ai plus 1 over ai, right? The absolute value of that. Again, on numerator, wherever you see I in the general term, you replace I with I plus 1. So that's ai plus 1. Okay. On denominator, you have ai, right? In terms of x and so on. So this time, be careful the absolute value. We just know x is a number. We do not know x is positive or negative. Okay. I'm trying to say you have to keep the absolute value notation in here. Okay. And then simplify the same way. Here you have to include absolute value of x. It's because again you do not know x value is positive or negative. I want you to pay attention. This limit is taken when I goes to infinity. When taking this limit, you treat x as a constant. You treat x as a number. Okay, we have seen the idea before, right? As I gets larger and larger positive, the limit is 0. Of course, 0 is less than 1. So that's why the series converges to, the series converges for any x value. For x value of 3, for x value of 5, for x value of negative 10, for whatever x value. Okay. Which means, now let's recall the term. The interval of convergence of the series is all the real numbers. You can write the interval of convergence using the interval notation, the open interval from negative infinity to infinity, right? If a series is convergent, then the limit of every term, the limit of the sequence formed by all the terms is equal to 0. Okay. Using that conclusion, I want to give you an important limit. The important limit says the limit as I approaches infinity. You look at that series. So we have seen the series is convergent for any value of I, right? And then we take every term, the limit of x to the power of I, and then the denominator is I factorial. When I gets larger and larger, when I goes to infinity, this limit is equal to 0. You see, if a series is convergent, then the limit of the sequence formed by all the terms, is equal to 0 as I goes to infinity. This limit is true for any value of x. Okay, just write for any value of x. I mean for all x, for all the real number x. Okay. Actually, the limit is not too obvious if you just want to compute the limit. I will show you one particular case. Okay. Now, for instance, when x value is whatever number 7, then the limit as n goes to infinity, 7 to the power of I over I factorial. I mean as I goes to infinity. This limit is equal to 0. We are going to use the limit for some proof very shortly. Okay. Now I'll make some comments on this question. The series in the question is actually the Maclaurin series of e to the power of x. Now you see the interval of convergence of the Maclaurin series of e to the power of x is the interval from negative infinity to infinity. Very similarly, we can show that the Maclaurin series of sine of x and cos of x have the same intervals of convergence from negative infinity to infinity. It's called the alternating series test. Okay. Now look at some details. If you have an alternating series in this form, we have seen this -1 to the power of I representing the signs are alternating. I value of 0 will give you a positive sign, I value of 1 will give you a negative sign, and so on, right? In addition to that, now let's check some conditions. All the AS are positive, and then all the AS, all the sequence formed by AS is decreasing monotonically, so decreasing. Okay, and also the limit of AS is equal to 0. Under this condition, we can conclude the alternating series converges, or is convergent. Okay, now let's look at a particular question, a simple question to show you the meaning. In this series, now let's identify AS first. In this series, you compare the forms. In this series, AI is actually the sequence formed by 1 over I. Now let's try to list some terms in 1 over I. So be careful, I starting from 1. Okay. I value of 1 so determines I value of 1 determines a term, so which is 1, right? And then I value of 2 so determines a term 1 over 2. So can I write I value of 1 so determines a term 1, and I value of 2 determines a term 1 over 2, and likewise I value of 3 determines a term 1 over 3, and so on. I think you can see the pattern. Okay. In general, I value of anything determines reciprocal of I. Now let's check the conditions. These are the AIs. I mean 1 is actually A1, and 1/2 is actually A2, 1/3 is actually A3. Do not include any signs in AIs. Okay. Now let's check the conditions. Okay. All the AIs are positive. You look at the condition. Okay. 1 is positive, 1/2 is positive, 1 over anything is positive, right? And also the sequence is monotonically decreasing. It means 1 decreasing. It means the terms go smaller and smaller. Okay, you see 1 is bigger than 1/2, 1/2 is bigger than 1/3, right? These numbers, all the AIs are going smaller and smaller. This is what we meant by AIs are decreasing. Okay. You see that condition is satisfied. And also the last condition is probably the most important condition. Okay, you check the limit of AI. So we compute the limit of AI as I approaches infinity. In this particular case, we're trying to compute the limit of 1 over I. Each value of AI is 1 over I, right? As I goes to infinity, you see the limit is 0, right? As I gets larger and larger positive, 1 over I gets tinier and tinier, closer and closer to 0. So that's why the limit is equal to 0. Now you can see all the conditions are satisfied. If that's the case, then you can conclude the alternating series converges. Now we are ready to talk about this. You look at the screen. So here we actually have a power series. Each term is written as a number times a power function of x. Okay. Now we are trying to determine the interval of convergence. By that we mean for what values of x the series converges. In almost all cases, to determine the interval of convergence or the radius of convergence, in almost all the cases we use the ratio test. Okay. To use the ratio test, identify AI first. Identify AI, the term determined by the index value of I. Okay. Identify AI first, and then we compute the limit of the absolute value of the ratio AI plus 1 over AI, right? I hope this one is not too complicated, but the idea is where in order to get A sub I plus 1, wherever you see I in here, you replace I with the I plus 1, probably in brackets. So do you see the numerator? If you replace I with I plus 1 in brackets, you have the numerator, right? And then the denominator is AI. I removed the signs because we are taking the absolute value. With or without the sign, the same thing, right? If you include the sign, I believe the sign inside should be negative, but you can remove it because the absolute value. Okay. Simplify a little bit. So do you see this 2i plus 3 is coming from here? You look at mouse cursor. 2 times I plus 1 and then plus 1, you have 2i plus 3. It's here. Okay. And then this numerator 2i plus 1 is coming from that. You just interpret the big bar as a division, invert and multiply. Okay. And then on numerator you have exponent of 2i plus 3. So do you see it here? 2i plus 3 exponent. Exponent here is 2i plus 1. And then x to the power of 2i plus 3 divided by x to the power of 2i plus 1. You subtract exponents, you have x squared. I'm trying to say 2i plus 3 minus 2i plus 1. 2i plus 1. The answer is 2. Right? That's why you have x squared in here. This limit is taken when I goes to infinity, which means when taking that limit, you treat x as a constant. Of course, after getting the answer, you treat x as a variable. Okay. That's why we can leave x squared out of the limit notation, right? And then you take the limit. We have seen the trick many times. To take a limit like that, you divide the numerator and the denominator by I. that term becomes 2, right? So it's that term. This term becomes 1 over I. This term becomes 3 over I. Okay. And then the limit as I goes to infinity, you look at mouse cursor. The limit of that term is equal to 0. As I gets larger and larger, 1 over I gets closer and closer to 0. And so is that term. I'm trying to say the limit of that term is equal to 0. Eventually, the answer to the limit for the ratio test is x squared. Okay. This is the value of L in the ratio test. You see the limit of the absolute value of the quotient is equal to L, so the L value is x squared. That's why the series converges if the value of L x squared is less than 1, and it diverges when the value of L x squared is greater than 1. And this is equivalent to the series is convergent when x is in between the -1 and 1. Okay. Which means the radius of convergence is equal to 1. And also diverges when x is outside the interval. I mean, when x is greater than 1 or less than the -1. So that's the meaning. Okay. So the radius of convergence is equal to 1. So we have seen that. There remains only 2 points. I will show you the meaning. Okay. So now let's say the origin is here. So -1 is here. 1 is here. We have seen the series converges when x is strictly in between the two numbers, so -1 and 1, and diverges when x is greater than 1 and less than so -1, right? There remains only 2 points, the 2 circled point. We have to determine. To determine the convergence of the of 1 and a -1, we are going to use the alternating series test. Alternating series test. Okay. Now let's take a look at some details. When x value is 1, you plug 1 into the series. So do you see the series becomes that? Wherever you see x, you replace x with 1. Okay. In this particular case, if you want me to mention some details, I'm telling you I'm going to use alternating series test to determine if that series converges or diverges. That's why you need to identify AI. In this particular case, do not include the signs. Okay, AI is formed using 1 over 2i plus 1. I will show you some particular terms. Okay, so now let's say a0, I starting from 0. Okay, so now let's say a0 is equal to a0 is determined by I value of 0. You plug I value of 0 into here, is a0 is 1, right? And a1, again in AI you do not include term, you do not include signs. I mean, okay. A1 is equal to 1/3. You plug 1 into 2i plus 1 over 2i plus 1. I think you see 1/3, right? The term after that is 1/5, I believe. This pattern goes on and on forever. Okay. Now let's recall, in order to use the alternating series test, we need to check 3 conditions. All these numbers are positive. 1 is positive, 1/3 is positive, 1/5 is positive, right? Obvious, right? The second condition is that these numbers are decreasing. You see 1 is bigger than 1/3, 1/3 is greater than 1/5. It's obvious, so these numbers are decreasing. By that we mean getting smaller and smaller, right? And one more condition we need to verify is to compute the limit of AI. Now let's say AI, the limit of AI as I goes to infinity is actually the limit as I goes to infinity. The limit of AI is 1 over 2i plus 1. You see as I gets larger and larger, the limit is equal to 0. So we have seen all the three conditions are satisfied. We can conclude that series converges, which means the series converges at this point 1. Alright. There remains only one point to check when x value is -1. But you plug -1 into the given series, the numerator will become -1. I'm trying to say 91 to the power of 2i plus 1. 2i plus 1 is always an odd number. 91 to the power of 2i plus 1 is always 91. And then you combine 91 to the power of I and 91, you have 91 to the power of I plus 1. Using very similar arguments, you can see that series converges too. Converges as well. Now you can see it in here. On the number line, we can include these 2 points in the interval of convergence, right? So you see the series converges for any number in between 91 and 1, including the 2 endpoints, and diverges outside the interval. Okay, so that's why the given series converges if and only if x is in between 91 and 1. By that we mean the interval, the closed interval from -1 to 1 is the interval of convergence. Now I want to make some comments on this question. The series in the question is actually the Maclaurin series of inverse tan of x. Now we know the interval of convergence of Maclaurin series of inverse tan of x is the closed interval from -1 to 1. In particular, the 2 endpoints are included. Now we are ready for part 5. I will do only one of the 3 questions. In the textbook, you have the proof for item number 1. Now we'll do item number 2. If you know how to do item number 2, then item number 3 is very, very similar. Now we are going to show that the Maclaurin series of sin of x indeed converges to the function sin of x. Now the proof. In order to use the formula, we introduce the function notation f of x. We use f of x to denote the function in the question, sin of x. You need to recall something from last week, what we mean by a Taylor polynomial of degree n at some a value. In this particular case, we're talking about Maclaurin series, so the a value is equal to 0. We're going to use t sub n of x to denote the Taylor polynomial of degree n at a value of 0. Initial term, the value of the function at 0, and then plus the derivative of the function at 0 times x minus a value is 0, so times x. I'm going to write a few more terms so that you can see the pattern. The double derivative of the function at 0 over 2 factorial and then times x squared. The next term, the triple derivative of the function at 0 over 3 factorial and then times x cubed. You keep on going until you have term n. I call that term 0, term 1, term 2, term 3 until you have term n. Term n is in the form of nth derivative of the function at 0 over n factorial times x to the power of n. You see that's indeed a polynomial of degree n. Now let's recall what we do next is to determine these values, the coefficients. I mean to determine f of 0, f prime of 0, and so on. Okay. But before that, for sine of x, we need to differentiate the function many times. Now let's work on that. Okay. The function is sine of x, and then we have seen this a few times already. The derivative of the function is equal to cos of x. The derivative of sine of x is cos of x. Okay. And then you keep on going. The double derivative of the function is negative sine of x. The derivative of cos is negative sine of x. And then the triple derivative of the function is the derivative of negative sine of x, so which is negative cos of x. I will write one more. And then the first derivative of the function, I'm going to write a little 4 in here to mean you keep on doing differentiate the function 4 times, equals the derivative of negative cos, which is sine of x. The derivative of cos is negative sine of x. So you see we're cycling back. And then in order to get the Taylor polynomial of degree n, we need to evaluate the derivatives at x value of 0. The value of the function at 0, sine of 0 is equal to 0, right? And then the derivative of the function at 0, it means cos of 0. You plug 0 into cos of x, you have cos of 0. Cos of 0 is equal to 1. And then you keep on going. The value of sine at 0, sine of 0 is equal to 0. Cos of 0 is equal to 1. You just keep on going. So we have the double derivative of the function at 0 is equal to 0, and then the triple derivative of the function at 0 is equal to negative 1. And lastly, so not lastly, you'll have to keep on going. Fourth derivative of the function at 0 is equal to 0. Okay. So this time, in order to prove item number 2, we are not going to remove the terms with coefficients of 0. By that I mean we are not going to remove any of these terms. We just keep the form of the Taylor polynomial of degree n. will show you what I mean. So t sub n of x. Of course, you have to keep on going, but you have seen the pattern after cycling back. So t sub n of x is equal to the value of the function at 0 is equal to 0, and then plus this term, the derivative of the function at 0 is equal to 1, and then plus x. The next term is 0, and then the term after that, term 3, is given by negative x cubed over 3 factorial. You see the triple derivative of the function at 0 is negative 1. That's why you have the negative sign here. And then you keep on doing. And then plus 0. I'm going to write one more term. And then plus x to the power 5 over 5 factorial. You keep on going until you reach term n. I'm just going to use this form. You look at the mouse cursor to denote term n. So term n is the nth, so derivative of the function at 0 over n factorial, and then times x to the power of n. Okay. Again, this one is called the Taylor polynomial of degree n above a value of 0. For this proof, we need to observe some other things. The function is sine of x. Sine of x is always in between -1 and 1. So the absolute value of the function, which is the absolute value of sine of x, is always less than or equal to 1. Likewise, the derivative of the function is cos of x. So the absolute value of the derivative is equal to the absolute value of cos of x, which is always less than or equal to 1. I said always, by that I mean for any value of x, the derivative of the function is less than or equal to 1. You can see the same thing is true for any derivative. I will just write the general form. Any derivative of the function at any value of x. This one is either the absolute value of sine of x or the absolute value of cos of x. So it's always less than or equal to 1. That's another fact I'm going to use later for the proof. We're almost ready. Now let's recall something else from last week. This Rn of x. Rn of x is called the remainder. Last week we mentioned Rn of x. You can see that from this formula. Rn of x is called the remainder. It's defined as f of x, in this particular case sine of x, minus t sub n of x, the Taylor polynomial of degree n above 0. We have also seen the theorem last week. Last week the notation I was using was C. this remainder can always be written in that form. This formula is called the Lagrange remainder formula. I said Lagrange. This value of c in general is between a and x. In this particular case, because a value of 0, so this c is always in between 0 and x. This is how you can represent the remainder in here, using a closed form. We'll prove that the Maclaurin series of sin of x indeed converges to sin of x by showing that the limit of Rn of x approaches 0 as n approaches infinity. I was using c in here. Now we use the form of the Lagrange remainder formula. Rn of x, I just copy it from there, equals n plus 1, the derivative of the function at c, and then denominator you have n plus 1 factorial. A value is equal to 0, so you have x to the power of n plus 1. Intuitively, the reason that the limit of Rn is equal to 0 as n approaches infinity is that the denominator, the factorial of n plus 1, is gigantic when n is large. In order to show the limit of Rn of x is equal to 0, we are going to take the absolute value of Rn of x. The absolute value is always greater than or equal to 0, so it's that. Now we are going to make this term a little bit larger, but not too large. We want the limit is equal to 0, so that's the idea. Of course, here you need to write c as a number in between a and x. C as a number in between a and x. In this particular case, a value is equal to 0, so you just say something like c is between 0 and x, again we are going to make the term a little bigger, but not too big. In order to see what's going on, I'm going to regroup the factors in slightly different form. I mean, equals we'll leave out the numerator. By that I mean you have that term on the numerator, and then you have x to the power of n plus 1 on top, and then I'm going to put n plus 1 factorial at the denominator. Taking the absolute value, so you have the absolute value of that, and then times the absolute value of that quotient. Now let's recall we mentioned earlier, it's here. Any derivative of the function at any value of x is always less than or equal to 1. In particular, the first factor in here is less than or equal to 1. This is the absolute value of either sine of x or cos of x at c. So I'm going to replace the first factor with slightly larger number of 1. And then the whole thing is less than or equal to, on the numerator you have x to the power of n plus 1. On the denominator you have factorial of n plus 1. So probably it's easier if I write the thing in this form. The numerator, I'm going to write that as the absolute value of x to the power of n plus 1. And then on denominator you have factorial of n plus 1. The next thing we're going to do is to take the limit of the right hand side. Now let's recall a limit we mentioned before. This limit is the limit as I approaches infinity. The numerator you have x to the power of I. On denominator you have I factorial. This limit is equal to 0. So we take the limit as n goes to infinity. We want to take the limit as of the quotient. The numerator is absolute value of x to the power of n plus 1, and on denominator you have n plus 1 factorial. Now all we need is to, from this formula, you can replace I with n plus 1. So as n approaches infinity, x to the power of n plus 1 over factorial of n plus 1 is equal to 0. So we have this limit is equal to 0. Now you see the remainder is a function in between 0 and that. And the limit of the right hand side is equal to 0 as n approaches infinity. And by the way, when taking the limit, the limit is taken with respect to n as n goes to infinity. So when taking the limit, we treat x as a constant. So the limit is equal to 0. Now, by the squeeze theorem, we can see the limit of the remainder is equal to 0. The limit of the remainder as n goes to infinity is equal to 0. At this point, we are kind of done, but to convince you more, I'm going to write a few more lines. Now let's recall we mentioned before. This t sub n of x, the Taylor polynomial of degree n at 0 in this particular case, actually is the partial sum of the Maclaurin series. So all the t sub n of x, for all n's form the partial sum sequence. In order to show the Maclaurin series indeed converges to the given function, now all we need is to take the limit of t sub n of x, to take the limit of the partial sum sequence. We'll do that. But before we do that, we want to write t sub n of x in terms of the given function and the remainder. You look at that formula. You look at the mouse cursor. Okay. So t sub n of x equals f of x minus the remainder Rn of x. You see that from here, right? And then we want to take the limit as n goes to infinity. We want to take the limit of the partial sum sequence. This thing equals the limit as n goes to infinity of the difference between two functions. So now let's recall the limit of as n approaches infinity, the limit of the difference between two functions is equal to the difference between two limits. So we can write that as the limit as n approaches infinity, the limit of the function, minus the limit as n goes to infinity, Rn of x. Now the limit is taken as n approaches infinity. So when taking that limit, you treat x as a constant. I mean, you can treat the whole f of x as a constant because this thing is independent on n. So the first term is just f of x, and then we have seen the limit of the remainder is equal to 0. So it's minus 0. So the whole thing is f of x. You see the limit of the partial sum sequence of the Maclaurin series of sine of x. The limit is equal to f of x. In this particular case, sine of x. This means the Maclaurin series of sine of x indeed converges to sine of x. Now I want you to see the entire proof is valid for any value of x. So I can add for all real numbers x in here. Now we can draw the final conclusion. Therefore, we can write the following equation with confidence now. The following is Maclaurin series representation of the function sine of x. Sine of x equals, I'm going to remove all the 0 terms. Remember this? The sum I from 0 to infinity, -1 to the power of I. On numerator you have x to the power of 2i plus 1. On denominator you have 2i plus 1 factorial. The equation is valid for any real number on the interval of convergence.